Okay, define for me what a series is.
A sum of all sequence.
Okay. Okay, series is a sum of terms. Okay, what is a geometric series? What?
Terms with common ratio.
Okay, a sum of terms that have a common ratio. These are all numeric, right? Numbers only. We started at the end of your homework last night playing around with, well, what if the multiplier is a variable, like an x, like sine of x, or something like that. Okay, that is a power series. A sum of algebraic terms. Okay, so then you have a geometric power series. So a sum of algebraic terms that have a common ratio, and the ratio is in terms of x. All right, so you need, that is going to be one of your cards. So get out your note card. Geometric power series. On that note card, you also want to put that the same rules that apply to a geometric series also apply to the geometric power series, only we write it like this. If r of x is between 1 and negative 1, if it falls within the interval of convergence, so therefore r of x is now an expression based on x. So that is true. Then we can still find the infinite sum, which would be a sub 1 over 1 minus r of x. So it's just expressed as a variable instead of expressed as a specific number. All right, additionally, you could put a little like approximation symbol. That sum will be the same, approximately equal to the value of the series of the function. Okay, it's just a much easier way to write the function instead of writing it out as its individual terms all the time. You can come up with an expression that is the same, equivalent. Yeah. So here is a geometric power series. If n starts at 0 and goes to infinity, and we have 5x to the n, our exploration leads us to terms that are 1 plus 5x plus 25x squared plus 125x cubed, etc. We can identify that the ratio, the r dependent on x here, is the multiplier 5x. And in order for this to converge, that 5x must be bounded between 1 and negative 1. Therefore, this series will converge if and only if x is between negative 1/5 and 1/5. So this is called the interval of convergence, like we talked about in our homework. If x is between that interval of convergence, then the infinite sum of this would be 1 minus, over 1 minus 5x. In other words, what we're saying is that 1 plus 5x plus 25x squared plus 125x cubed plus infinitely many terms can be simplified to the single function 1 over 5x. That those two things are essentially the same thing, which is going to be hugely helpful to us. They are replaceable now. They are interchangeable, one without the other. So would you rather find the derivative of infinitely many things, or would you rather find the derivative of one thing? Infinite. Okay. Would you rather find the integral of infinitely many things, or would you rather find the integral of one thing? Okay. And so we're going to use this property to help us do the derivative and the integrals of sums of series. Yes? Mm-hmm. Mm-hmm. Okay. Here's another geometric power series. We have n equals 0 to infinity, negative 1 to the n, and x plus 2 to the n. Now some people might look at that and go, alternating, it's got negative 1 to the n, it's going to alternate. Okay, but that's going to behave differently because it's got a power, it's got a variable in there too. What is, let's just go through the math here, what is the constant multiplier going to be? Okay, they're both to the n power, right? So it'll be negative quantity x plus 2. Okay, let's apply the interval of convergence to that. Okay, divide everything by negative 1, which flips the signs around. Subtract 2 from everything. Oops. All right, this, x being between negative 3 and negative 1, this is the interval of convergence. So this is where an alternating series can still converge if the values of x are between negative 3 and 1, this series will converge. If the values of x are outside of that interval, the series will diverge like all alternating series do. So an alternating series is not a slam dunk for divergence. If it's a power series, which is involving variables, we can limit our x to a certain interval of terms, and then it will converge. What will it converge to? Okay. All right, the first term would be 1. Yep, over 1 minus negative x plus 2. We've got double negative going on there. So 1 over x plus 3. So this series, as long as x behaves within the interval of convergence, will converge to the function 1 over x plus 3. You might hear language like, this is a centered interval, okay? Like, you know how, like, find your center, right? Whatever. Okay, what is the center of this interval? The interval of convergence, where is the center? It is, -2 is right smack dab in the middle. And so sometimes you'll hear centered at -2. How far off from -2 do we go? Right, in both directions, okay? And so then we'll say with radius ±1. So that's another way to say the interval of convergence. The interval is centered at -2 with a radius of ±1. So then you know you're going from -2 up 1 and -2 down 1. And that's just another way of saying the exact same thing. So you could write it out like that, or you could do it in inequality notation. All right, that leads us to our next big idea for today, which is our second flashcard for the day. And this has to do with integration and differentiation. Okay. Differentiation and integration for geometric power series. Okay, so if the sigma, the sum to infinity, if it converges to f of x, which means it had to have met the convergence rules that we just did. Okay, so if it converges, so you can maybe, then we can go both directions on this. Then the derivative d dx of the sigma can be found by f prime, and the integral of the sigma of the series dx can be found by the integral of f of x dx. And so you can both differentiate and integrate a geometric power series by finding its function approximation and then just applying your derivative and integral rules to that. Hugely helpful. Oh no. Okay, hang on. Okay, let's try it. Sorry. Oh, okay. Add this to help you with your bounds. Let me just change colors here. Okay, your bounds are going to be c to x for both of these. C is where it's centered at. Okay, that's how you determine the lower bound, is the place that the integral is centered, or the interval, excuse me, is centered at. So if it's centered at 0, your lower bound will be 0. If it's centered at a different number, then that becomes the bottom of your integral, lower bound.